Yeah, we'll probably talk about it even more briefly. No.
Even more briefly?
I assume so.
Can I ask you something about one of these homework problems?
Yeah.
It's to, this was to determine, it was the question on the homework to determine like the freezing, the moles of
Oh, yeah.
the sugar from the freezing point, kind of. And so the way I set it up, I did that equation, the molality times that constant that I forgot what it was called, times equals the change in temperature, and then the molality equals the moles of the solute over the kilogram solvent, that those were the givens. And then there was 100 milliliters of the solvent, that is water, so that is equal to the 0.1 kilograms. And then I set it up like this,
Yeah.
and
Looks
I
good.
got I got 5.03 for the molar mass, but on the answers for the homework it was times 10 to the negative 2.
I would just double check your math. I have to pull up the homework. You should complain about that to everybody.
It doesn't make sense. If I fail lab, I have to repeat the whole class? How does that work? Just because I did a little thing wrong.
You should write these complaints up in writing. I don't know. It's like you could start with what class is it?
It's biology. Yeah, I mean like.
Yeah.
The sciences that are split now, but.
Yeah.
I don't like that. It's just so much work when it's only 1 credit class.
Oh, yeah.
And like, it's still 2 or 3 credits worth of volume, but like you just have the point values.
I would just like send an email, start complaining to like Navarro or something, or like your other dean, because you have April Hamlin's like your student dean, right? Because she's supposed to be the dean of student success, right? That's why you guys got to get involved in your college, because all the professors we're against splitting them, but.
Is chemistry that way? Is the.
Shh.
Okay.
It's supposed to be, but I'm not doing it, because then it'll just, it screws everything up. So we're split. Yeah, that's how that goes. And if anybody from administration asks, yes, we're split. But yeah, you should start complaining, because all the instructors were all like, why do we have to split up? And then admin's just like, you have to. Like, that doesn't make sense. Yeah, but if the students complain, then that has more merit than the faculty trying to be like, yes, the students don't like it. But, so y'all gotta complain.
I will complain. I'll write a strongly worded letter.
Yeah. Definitely write strongly worded letters to everybody. There's also the chats with Randy, which you could always bombard him. The next one, though, is on the Table Rock campus. Those are always other ideas. Just get hordes of angry students. All right. So let's see. So 10.
And I'm like, and they're so it's like the point.
0.37. Oh, I already started off wrong. So you got like point, multiply it times 0.1. So that's how many moles, right?
Oh, wait. I think I think I see what I did wrong here. it was dividing by 0.1 and I got that mixed up, I
Oh,
think.
yeah.
I don't know, I just think it's really stupid, like, you're not fooling anyone, it's the same amount of stuff. Even though it's the yeah, right, yeah. So when it says the molarity of sodium hydroxide, you put
Funny. It should be moles divided by however many mils you use. So it should be the 3. But see, something looks funny already, because this should be a 1-to-1 ratio, right? So I think something looks off there, because these should be 1-to-1. So that should be the same, so then it should be 0.000128 divided by your volume. So that would give you closer to like almost 0.01, which is what we said.
Wait,
Point.
so what did I do wrong?
I'm not sure what happened from there to there, because that looks funny, because these should be the same number, and then you just divide that by the mils of NaOH used. So I get 0.0075 molar, which sounds better. But yeah, I don't know where that
So
came
my,
from.
so this was messed up?
Yeah, because these
Oh,
should be
wait,
the
I have
same
my,
number.
I have my equations. So I did sodium hydroxide, right?
But for this one, we're basing the moles of sodium hydroxide off of the KHP, right?
Why wouldn't I just calculate it based on the like,
But where did that come from?
oh, we used,
But we're trying to
365.
find the molarity, because we don't know the molarity. We can, because you're assuming that it's 0.01 molar, but we can't assume that. Because that's why we use the KHP to titrate it in the first place, to get it more precise, right? Because the stockroom said they made 0.01 molar, but that's not accurate. So that's why we use the KHP to figure out the true molarity of NaOH.
Oh, okay.
But yeah, we can
Oh,
talk.
yeah, I'll catch you up.
All right, let's go ahead and get started. And so before we finish up the solubility chapter, I forgot that a while ago we rearranged the order of the labs, I think to try to give y'all either a blank week and then extra time. But that meant that we had to do the titration early, so we haven't talked about acids and bases. So I'm going to go over question 7, but then also give kind of like a quick and dirty acid-base introduction. So we'll say our quick acid-base introduction. And so the trouble kind of starts, and let's just look at what we're given and kind of what the comparison is. And so we're told that we have a pH of 0.150 molar citric acid, or they're asking us to find the pH. And so now let's just start with, well, how do we find the pH just normally? Or what is pH? And let's just take instead, because we have to talk about the issue with the citric acid, but what if we want to find the pH, and we'll use the same number of a 0.150 molar HCl solution. And so the difference in these two problems is this is a strong acid, so this fully disassociates. And so this means, right, it disassociates into the two ions. And so then we can say, well, I have 0.150 molar concentration of H plus ions. And this is true, again, because it fully disassociated. And so then all we need to do for a strong acid is we can just plug in the molarity. And so you have this formula, so pH is equal to the negative log of H plus concentration. And so for our strong acid, we can just plug in the number that we were given. And so for our hydrochloric acid scenario, we just take negative log of 0.150. And double check your calculators, make sure they're in the right base set and everything, that they're in base 10. And so we would imagine that we should get a pretty low pH since it's an acid. So pH is 0.823 for our HCl. So is everyone at least okay with just kind of what's the basic formula for our pH? And so kind of the issue now is, well, now if we look at a weak acid, and so I'll write here, right, this is a weak acid, so it does not fully disassociate. So even though we have 0.15 molar concentration of citric acid, since only a part of it is going to disassociate, we're not sure how much. And so this is what's kind of laid out in this ICE table, or we'll call them RICE because I like to put the reaction there. And again, we haven't gone over it, so just kind of hang with me. But it's showing you the disassociation step and kind of modeling that. So right, first we have our equation. So we have our citric acid. And then it said, well, only consider the first disassociation step. And so again, this is what's shown here. One proton being disassociated, and then our conjugate base here. So this is H plus, right? And we can call this A minus for our abbreviation's sake. What's up? Well, so this is like how much is floating around disassociated. Because like, yes, it does exist in a pair, right? But again, when it's in solution, it disassociates. But then the problem that we're running into is, well, how much is this associated, right? So that's what we don't know. So that's what we're trying to answer. And so with this, we can set up what's called this Ka equilibrium expression. And so our Ka is just an expression. And so it's basically saying, right, for our equilibrium, it's generally products over reactants, which then we can rewrite for our scenario. So now it would be H plus times our A minus over our conjugated HA, which just translates to H plus times our base times our original concentration. So this is like the first key step. And so then all we have to do to solve for what it's asking for is we have to solve for x. And so then we can set that up by Ka. And since it's disassociating by x amount, right, so it's minus x for the original, and then HA and the conjugate base will both be an x in this case. And then so we can simplify it to something like x squared over then 0.150 minus x. And so if you didn't understand anything that I said, right, this is basically what you need to solve this problem. And then it gives you Ka, right? So then you can go ahead and solve. So we have 7.4 times 10 to the negative 4 is equal to this expression. So this is another good place to be. And so if you have a fancy calculator, some of you may be able to even just plug this in directly and solve. So kind of the tricky part, so this is a quadratic, right? So you could also solve it and do the quadratic, so you can do that. But I'll tell you a trick. So this is 10 to the negative 4th. And so we have this kind of rule or trick that we say if x is less than 5%, so we'll have to kind of double check this assumption. But usually if you see a difference of like 10 to the minus 3 or 10 to the minus 4 or greater, it's usually a safe assumption. And so I'm just going to make our assumption. So assume x is really small. And now this makes it even easier to solve. And so now we get this answer. And so let's just double check that. So 0.15 times my Ka. And then we can take the square root of that. So now this is x. So x is 0.0105. And then we can double check, make sure that it is less than 5% of our original, so divided by the 0.150. It's actually not safe to make the assumption. So now it's actually 7%, so now we have to do the quadratic. So it's kind of annoying. So we can't assume here. And so now we have to go back to this equation and solve for the quadratic. I'm just going to copy. So now this gets a little messier, but we just have to start by distributing. So I would multiply both sides by the 0.15 minus x. And then I'm just gonna move everything over so I can solve my quadratic. And you guys can help me. So did everybody get to this part at least? So we agree on the quadratic? And so now we just have to plug it into the quadratic equation. So do people remember the equation? So who wants to rattle it off? Go for it.
I think it's, I might be wrong in this, but I think it's negative b plus or minus square root of b squared minus 4ac over 2a.
All right, excellent. So now, right, so this is A, this is B, this is C, if we remember that. So A just corresponds to the x squared component, B is x, C is the number. And so now we all have to plug that in. And again, I know some of you have fancy calculators that do everything now, so that's fine. And so again, double check my numbers. I got this expression, and then I know it can't be the negative because we can't have negative values for x, so that doesn't make sense. So then I'll just do the positive, so 0.74 times 10 to the negative fourth plus 0.02108. Oh man, I meant to do plus. Sorry, let me punch that in again. Plus 0.02108 divided by 2. So did we get this for x? So now x is 0.01017. And so again, right, this is now the molar concentration for H plus, right? That's what we were solving for with that quadratic. And now that we finally solved for the concentration of H plus, aka, right, how much is disassociated, now we can plug it into the pH formula. So negative log of x, so that's the same thing for H plus in this case. And then, so we should get a pH of like 1.99 then, once we plug that in. So, questions about this process? Oops. And so just looking at the post-lab question, right, it should be pretty similar. So the only difference is then you're plugging in whatever molarity you found. So, right, we're trying to figure out, well, how much do we have? But then that's not telling us how much is disassociated. So you just plug in your concentration that you found for molarity. And then, of course, right, you can just set it up. So I'll kind of give you the setup, right? So Ka then is just x squared minus whatever molarity you found, minus x. Maybe you can make that assumption. Otherwise, you have to solve for the quadratic. And it's still the same Ka since it's the citric acid. So does that help you with the post-lab at least? And then was there anything else from that lab that was difficult or confusing with the calculations or anything? Were there other questions from like chapter 13 or anything? People are saying the gas chapter was giving them issues, but I didn't get any questions, so I wasn't sure what to cover. Or people just need to practice with the gas chapter more. Do you need more practice on anything specifically, like that I should look for some problems?
Nothing quite rings a bell, but I think the density one used to get me, but I guess the density within it.
Okay, I'll look for some examples, and maybe at the end of class I'll come up with something then. So density problem, other issues, or if not today, then I can keep it in mind for Tuesday of what to cover. So that's the other thing, semi-topics for Tuesday, so we can review. Again, I'll have my set review, but if there's anything else burning. All right, let's finish up our chapter then, or at least see how far we get in our chapter. And so again, right, we were talking about our colligative properties, so properties that depend on how much is dissolved. And so you may have heard of osmosis before. And so, right, osmosis is just defined as a flow of a solvent from a solution of low concentration into a solution of high concentration. And so generally it's separated by some sort of semi-permeable membrane that usually allows like water to pass through, and then the ions cannot. And so now we can look at what happens. So we have our little scenario here. So we have our initial setup. And so notice the right side is all water molecules, and then on the left side it's water molecules plus some solute particle. And so if we just leave this alone, then our water level on the left rises, right, as it goes from our low concentration to our high, trying to make those two concentrations equal. And so now we can also measure the pressure, just like we've done before, right? We've seen water level rising with our height of the water column. So you can also measure this pressure similarly, and so our pressure of our excess fluid, so the height that it rose, is related to our osmotic pressure. And so then osmotic pressure then is just defined as the amount of pressure needed to keep the osmotic flow from taking place. And so it's proportional, of course, to the molarity. And so they have, right, osmotic pressure is equal to molarity, and then times our R, so this gas constant, times our temperature. And sometimes you might see this alternative form. Alternative. And sometimes they add in this I factor to remind you, right, of the Van Hoff. So it's just basically saying, right, take into account how much it disassociates. So just don't forget that. So again, right, this is essentially our effective molarity in solution. So we have to take into account how much it disassociates by. And for our purposes, we generally don't calculate the pressure itself, but we just kind of compare, right, which one has a higher osmotic pressure. We can go back to the question.
Throwaway symbol for pi?
Yeah, this is a big pi, capital Pi, but that's just the osmotic pressure symbol. Other questions about just this? And so these are good, yeah.
Sorry, I just want to make sure that osmotic pressure symbol isn't
No, it's, yeah, well, it's capital Pi.
Oh, I see.
Yeah, so this is capital Pi.
Okay.
And some important things to know are these little terms. So osmotic or isotonic and hypertonic. So let's go through all of these. And so if we have, and we can call it either an isoosmotic solution, so that would have the same pressure, or generally in chemistry we use the term isotonic. And so isotonic or isoosmotic, that's when your solution has the same osmotic pressure as the solution inside the cell. So no net flow of water in or out. So this is what you want to be normally, right, in equilibrium. And so let's look at these other scenarios. So we have the hyperosmotic solution. And so a hypertonic solution can occur when you have a higher osmotic pressure than the solution inside the cell. So as a result, your water flows out of the cell, causing it to shrivel, right? So, right, our poor cell is trying to make our blood or whatever less salty. So maybe this could happen, you know, if you have too much salt in your diet, and again, this would be like extreme, but that could potentially would happen to your cells, right? It's like kind of shrivel up a little bit as your blood is too salty. And then so the opposite would be hypoosmotic or hypotonic, so lower. So your solution has a lower osmotic pressure than the solution inside the cell. So then there's a net flow of water into the cell. And so with this one, I always think of like the gallon challenges and why those could be dangerous. And so, right, what could potentially happen when you do like those gallon chugging competitions is right now you just have a bunch of water, so that dilutes down the blood in your bloodstream. And so right now they're trying to go into the cells then to try to equalize that, and so that would cause your cells to swell or potentially even burst. So that's why those gallon challenges can cause like brain damage and all sorts of things just from drinking water, which is kind of crazy.
What if you drank a gallon of salt water?
I mean, then it's the question, are you going to get the hyperosmotic solution, right? How salty is that salt water?
What if it was like the perfect level of salt?
I mean, then you might be fine, right? As long as you're drinking a isoosmotic solution. So yeah, that might be different, but I'll let you play with your body salinity like that.
Yeah.
But yeah, that goes into, because you could also talk about like distilled water, right? That's why you shouldn't drink too much distilled water either, because that can leach your body of nutrients. You know, you need those magnesium ions and all those good things, calcium. All right, so now let's look at back to our volatile solutions. So this kind of goes back to what y'all were thinking of, well, what happens if we add kind of a more volatile solute to our solvent? And so let's go back to that. And so now we're talking about when both our solvent and solute can evaporate, well, right, you guys have surmised, well, of course, then both molecules will be in the vapor phase. And so again, answers a lot of the questions you were asking. So now how do we know what's the pressure? And so we have, so in just an ideal situation, right, we would, just ideally, that means the solute-solvent interactions would be equal to the sum of the broken solute-solute and solvent-solvent interactions. And so then this would just mean that the vapor pressure, again, for an ideal solution, would just be the sum of the vapor pressures. So, right, we would just might imagine, again, if they're not interacting, we would just have our total pressure, and then we would add, right, the components, our solute and then our solvent pressure components. And so, right, then we could say, well, the solvent decreases the solute vapor pressure in the same way the solute decreases the solvents. So this is just from before, right? So we had said, well, we can find the pressure of our impure solution, right, by taking the pressure of the pure solution and multiplying it by the mole fraction of each one. So that's all they showed there, right? So this is how you would get the ideal total pressure. So just finding our mole fractions, right, figuring out how it would be affected, and then adding it. Does that make sense so far? Okay, don't scroll yet. Perfect. So yeah, just take that in. So, right, this is just repeating, again, what we said on Tuesday. Okay, are we ready? Some people might still be copying. All right, so now let's see what it's saying. And these charts are pretty helpful. And again, this goes back to what you were asking, because you're like, well, you know, do they just add? Could they potentially be higher? Could it be lower? And so that's exactly what Raoult's law is saying. And so let's just look at all these scenarios. So our first picture is, again, just with our ideal scenario and how we expect, just from what we learned. So again, we take our partial pressure of our components, and then they would make a nice additive line, and everything would be fine. So let's look at this case here. So what if you have strong solute-solvent interactions? So therefore, right, that they're interacting kind of more strongly than just the solute-solute or solvent-solvent interactions. And so we see if the solute and the solvent interact really strongly together, you're going to have a lowering of your overall vapor pressure. So it would just be a deviation from your ideal Raoult's law. So, right, they would not add, and it would be lower. So then you would find, oh, this is telling you then that we have a strong solute-solvent interaction then if it's lower than what we expect. Does that make sense? So we'll just be determining, so do they have a strong interaction, or alternatively, right, what if you have a weak solute-solvent interaction, right? So they're not mixing as well, and so that would result in a higher vapor pressure than from what you would expect from just the additive. So we'll go through an example, and I think that'll make more sense. And so that's all this text is showing. So again, right, if you have strong solute-solvent interactions, and again, stronger than either one by themselves, then that's where we get a lowering of the vapor pressure, versus if they're weaker, then the total vapor pressure will be more. All right, so let's go through this example, and that'll make things more clear. So we have a solution contains 3.95 grams of carbon disulfide and 2.43 grams of acetone. And so it tells you the vapor pressures at this temperature are 515 and 332. And then assuming ideal behavior, calculate the vapor pressure of each component and total vapor pressure. So this is what we want to be able to do. So again, we'll assume ideal behavior. And then we would need to know from our problem what's experimentally found. So once we get our answer, we'll go back and compare it and then be able to determine if we had strong carbon disulfide acetone interactions or weak carbon disulfide acetone interactions. So take a few minutes to at least try to get started on this, and then we'll go over it. So let's at least start going over it. And we're kind of running out of class time. So what do we need to do first here? So moles. Do we have a molecular weight of carbon disulfide? Do people like that number? Oh, I might have had audio. 76.143. Does that sound good to people? And then, do we have a molecular weight for acetone? 58.0. 58.08. Okay, that looks like confirmation. So exactly, so now we need to find our mole fraction of each. So I'll start with our CS2 and finding moles. I guess I need to find just moles of each before I even go to mole fraction. So did we get 0.0519 moles of CS2? It's like 0.0519 moles. And so let's see what we get for acetone. So we get like 0.0418 moles of acetone. I see some yeses. All right, so now we can get our mole fraction. So we'll start with our CS2. So moles of CS2 over total moles. Oops, almost dropped my 0. 0.048. And then, so while I'm doing this, I'll multiply it. So it says our vapor pressure is 515 torr. So I'll multiply that. Keep dropping my zeros. So double check my math for me. So I got a mole fraction of 0.55 for,
So for the acetone one, on the bottom, what number is that?
0.0418, and I think
No, I
that's,
mean for like the mole, grams per mole for acetone. Is that
Oh.
55 or is that 56?
I think we had said 58. I don't know if that was a little, I didn't double check it, but I know 2 people said 58. So about 0.55 times 515. So I have about 285.3 torr just from the CS2. And so now let's do our mole fraction for acetone and repeat that, except multiplying by the vapor pressure of acetone. And of course, acetone's vapor pressure is 332. So we could also do 1 minus our mole fraction, so that should give us the same answer. And then multiply times 332. So about 148.13. So now I'm going to add them. So I have a total pressure of 433 additive. So now this is our ideal pressure, so everybody got that at least. And so if once we're here, so now it goes back, and so it says experimentally it was 645 torr. So now what can we tell about those interactions? So they're weak, right? So this, the actual is higher than expected. So they said it was 645, so yes. So now we can say our acetone and carbon disulfide interactions are weaker than expected, since it was a higher vapor pressure. Excuse me. Any questions on that problem? All right, so in our last bit of time, there's another little equation. So this isn't too bad. So kind of like our proportionality constants for freezing and boiling, right? We have the same sort of thing. So now we have our Henry's law constant and figuring out our solubility of gas. And so for all these, again, this is one of those scenarios where every gas has their own KH constant. So on an exam, I'm going to be providing this for you. And so again, just note the units. So again, they're related to solubility. And so it's trying to figure out, well, how much gas can you get in there? And so it's given in moles per ATM for our solubility. Again, we have our gas constant. And then it's just telling us, well, what pressure is like a soda can pressurized under, right, to get an appropriate amount of solubilized CO2 in this case. And so the other kind of big concepts that we need to know is also how things solubilize in gas differently. And so, right, we can say, well, solids, when we dissolve them, so in general, right, you increase the temperature and the solubility, again, in general, increases. Solubility increases. So that's for solids, right? Dissolving solid thing in an aqueous or organic solution. And so what's awkward is, so gases are the opposites. You might want to write that. So gases are the opposite of how solids behave. And so first they give an explanation, right? So we have to recall, well, gases are generally nonpolar, and so they have a much lower solubility to begin with than our like ionic compounds or polar covalent molecules, right? Because those can maybe hydrogen bond a little, they'll have a little polarity, or again, those ionic ones, they can fully disassociate. And so we usually don't have high solubility with gases. And so again, once we increase the temperature, the solubility of the gases decreases. And so that's also because, right, we don't have very strong solute-solute interactions. So, right, your gases, again, they're not really interacting, or at least they don't tend to, so we don't have to overcome those solute-solute interactions. So that's why we have this inverse relationship. And so we could see this with our soda. And it's right, if you have a cold refrigerated soda and then you pour it out, you won't see a lot of bubbles bubbling out, versus if you pour like a warm soda out, it'll be a lot more fizzy as all those gases escape at those higher temperatures. And so, of course, how do we make our solvent hold more solute? Obviously, we can vary the temperature, or in our canning case, right, we can increase the pressure. And so we can make our solution saturated or unsaturated by changing, of course, our temperature and pressures. And so we can think about this with our shaking our carbonated beverage, and then, right, that can cause it to spew everywhere since we make our supersaturated solution unstable. All right, let's do, so I think this is the end of our chapter. I'm just double checking. Yep. So this is our last bit, so we'll end on this. So what pressure of carbon dioxide is required to maintain the carbon dioxide concentration in a bottle of club soda at 0.12 molarity? And once you copy this down, I'll scroll up so we can grab the KH constant. And then, so I'll scroll up for the KH constant. So if we're looking at CO2, we need to grab this KH, so 3.4 times 10 to the negative 2, and then multiplied by this.
Units of pressure is the KH constant.
ATM, so yeah, I wrote the units.
Is there a specific unit that you want in the pressure unit?
We'll just keep it, because, right, the KH, at least when I'll be providing it to you, we'll see it in molarity per ATM, so you can just leave it in the ATM. All right, let's hear what you got. So, right, it told us our solubility that we were desiring, so 0.12 molarity. We were given our KH, so we just had to solve for pressure. And like I said, it basically just depends on what unit you're given your KH constant in, but in this case it was an ATM. So what did y'all get for your pressure? What did you say? 3.529 ATM. So about 3.5. So that sounds good, and I can finish plugging that in. Yeah, those are not too bad. Again, we can use our dimensional analysis to help. Perfect. Any questions on this one? We should probably round it to sig figs. Any other questions for now? All right, so we'll stop there. We'll go ahead. I'll hand out the quiz and then ask questions. I can help y'all with the lab. Oh. It's something to just know. I don't think we're going to be quantifying that. I would have to look up if there is. an equation that relates it, but yeah, just for our purposes, know that if you increase the temperature, that decreases the solubility of the gases. All right, we will end there. So if you need the quiz, if you're online, just email me, and I will hand this out in class.